In today's video, I plan to share with you a database management system that I have designed for a company called Indoor Plants Online. This startup is determined to make plants more accessible and interesting with the focus on ease of buying. Whether you have low lighting in your home or want plants of a certain size, IPO has all you need with the click of a mouse. Choose your plants and accessories and poof, they'll be on your doorstep in no time. This company needed a better way to manage their inventory, suppliers, customer profiles, plant and supply selection, and orders. The DBMS I've outlined for them will make generating sales reports, orders, and product management a breeze. Here, I am outlining the relational schema. A relation is a table with columns and rows, or rather, the outline for how the database will manage and organize the data. This diagram here contains all of the tables and their attributes that are essential to a company. The relations that are crucial to this business in particular includes plants, inventory, supplier, customers, orders, and supplies. To explain it further, take a look at the first line. Plants is your table. To the right of plant, you will see plant name, price, type, level of sunlight, water level, size, color, and lifespan. These are all attributes of that table. The attributes will make up the columns in the relation. It does not matter what order the attributes are arranged in. In bold, you will see what's called a primary key. This is the unique identifier for that relation. In the first example I gave you, plant name is the primary key for the plant relation, and it is signified by bold lettering. In italics, you will note what's called a foreign key. These are attributes of a relation that match the candidate or primary key of another relation. If you look at the relation inventory just below the first example I gave you, you can see that plant name is in both bold and italics. That is because it is the primary identifier for inventory, but the attribute also exists in the first relation, plants. This slide focuses on the transactions or functions the Indoor Plants Online company would need to perform in day-to-day operations. Generally, this would include sales, returns, and ordering supplies. More specifically, the functions can pertain to the addition or deletion of customers, and with that, any orders associated with their profile. This can be seen in Business Rule R2. Once a customer is removed from the system, any record of previous orders should also be removed. Otherwise, the order will no longer belong to anyone and just exist randomly in the system. This would generate an error if a query were to sort the orders by customer number. The business rules are the types of actions allowed on the data. This chart represents what's called integrity constraints. These essentially make sure that the data remains accurate. Foreign key constraints ensure the database knows what table the foreign key is referencing. A constraint is anything on the table that limits something. It references something else. Foreign key, plant name, has to refer to plant name from the plant's relation. For context, someone couldn't order a plant that isn't carried by the company. Therefore, any foreign key plant name in the orders relation has to match the primary key of plant name in the plant relation. This chart identifies the foreign keys and which primary key they are referencing in accordance to each business rule. The constraint then is called on-cascade delete. One cannot exist without the other. So once a plant is no longer carried, it will also be deleted from any orders and inventory because you can't sell something that you no longer carry. The entity relationship model focuses on the most important data, which would be the entities that I mentioned before, and maps out the relationships between them. It is a more generalized approach to the data and adds in information like attributes as additional information. As mentioned before, entities are the most critical data points for the company. An entity is a group of abstract or physical objects that exist in the real world. Inventory is a great example of a physical entity. At company headquarters, there is a warehouse full of plants and accessories that is critical to the company's operations. An example of a more conceptual or abstract entity would be the number of views on a house listing. You can't physically see all the views. That doesn't make any sense. However, it is still important data that doesn't have to have a finite existence. Just like the relational schema, the entities for Indoor Plants Online would be plants, inventory, supplier, customers, orders, and supplies. A better way to understand the ER model is to switch out the word relationship with the word has. The entity order has one customer number. The relationship here is 1-to-1, meaning that each order will have one and only one customer associated with it. There will be several relationships between the entities. Some will have more than one, and others might not have any connections at all. This is a physical representation of all the entities and their relationships to one another. As I previously mentioned, there are still constraints in the ER model. If a plant is no longer being carried, its spot in inventory and orders will also be deleted. This is represented in the binary relationships or the 1-to-1 multiplicity. The next idea I would like to talk about is queries. Queries are requests for data within the DBMS that comes from the tables you create. Using the structured query language, or SQL, you can call upon certain information which is generated as a result. In other words, a search and an answer. If we take a look at some of the queries I have generated below, I can explain what some of them do. Starting with number 1. In bold, we have the words select, from, and where. These are part of the structured query language. The first query is essentially retrieving data using select to pull from a specified table or tables, and the where is searching the rows for a certain specified condition. In this case, we are inquiring about the plant name and want to take this information from the inventory table because our where clause is asking the database to inquire about plants whose inventory is less than 5 plants. The only place that information can come from is the inventory table. This is a very simple select command and is one of the most frequently used ones. You can substitute inventory with the plant table and then ask the database to show you all the plant names that are listed to be purple in color. Looking at number 5, your from is now the plant table, and your where clause is showing the condition we are inquiring about is that the color must be purple. Skipping ahead to number 9, we can see a more complicated SQL command. This one requires a subquery. A subquery is a select statement that exists inside another select statement. In a way, you could compare this to the popular math trick PEMDAS, where P stands for parentheses. Usually you want to start by solving anything that is inside the parentheses in an algebraic equation, as you will use that to then complete the next order of operations, which would be multiplication or subtraction, etc. Back to queries. You will essentially need to solve the inner select statement in order to understand and solve the outer statement. The inner statement in this case exists in the where clause. In example number 9, we have to first identify the supplier ID by accessing the inventory table and pulling the plant name for the suppliers with the IDs 1001 and 1003. Once we have completed that, we can move to the outer statement and then inquire about the plant type and plant size of those plants from the plant table that have satisfied the supplier ID condition. This might be helpful when an amateur plant lover wants to get a small succulent plant that doesn't want to wait too long for it to ship. If we need to order more, we can identify the closest suppliers to our location and choose from their products in our inventory that fit the customer's criteria. Subqueries are another way to do join statements. The database management system I have designed for indoor plants online will launch this business into the 21st century and allow it to compete against the bigger corporations that dominate the plant market. They will certainly see an increase in productivity and efficiency that will impact every aspect of their day-to-day operations. Thank you everyone for your attention during this presentation. It was a pleasure to be your host. Have a great rest of your semester. Sincerely, Jade Chen.